Hi everyone, this is a video for geometry, Math 240, 341, and this is going to be an example of a reptile. This one actually winds up being a fractal, so it's pretty interesting. It starts out as this, I don't know what you call it, curve, which is really just 1, 2, 3, 4, 5, 6, 7, 8, 8 line segments, all of the same length, and they make sort of this heartbeat kind of shape, right? It goes up and down, up and down. And in fact, this curve is pretty easy to program, like in Logo, that kids can learn. So this is a nice example of something that you can do in lots of different venues, right? You can think of it as art, you can think of it as programming, coding, and you can think about it as math. So let's deal. So I was going to think about shrinking this. Notice each of these, there's 1, 2, 3, 4, 5, 6, there's 8 segments. But notice how many segments wide it is. It's really 1, 2, 3, 4. Because of sort of this kink in the middle, that's what's gonna give us the strange dimension. So if I take this thing and shrink it down by 4, so the whole thing fits between these two dots, and then make 8 copies of it, it would look something like this. So hopefully you can see here, it's the over, up, over, down, to, over, up, and over. And it's that and each of those 8 segments is replaced by the single guy. Right, again, let me show you here. It's over, up, over, down, down again, over, up, over. Okay, so notice this curve here, we got by putting 8 copies of the original curve. Each of the original curves shrunk down by 4, a factor of 4. So if I did it again and shrunk each of these things down and replaced it with 8 copies, it would look like this. And now you can start to see, I made a little mistake. You can start to see how wiggly it is. And it's pretty cool. I did this by hand, so just just the 3rd stage. And it's already pretty kind of nested up. And an important thing to note if you're trying to come up with these on your own is you have to make it so that when you shrink it, it doesn't bump into itself. So notice like this original one, you might think you could do kind of, some kind of arbitrary thing. But you can't, because this one here, it's going to wiggle somehow here. And then when you turn it, it's going to wiggle here. So you don't want this wiggle here to intersect this wiggle here. So you can't do it just anyway. And notice this is done just nicely enough so that this thing here, that this guy here, this wiggle, then when you turn, and then, sorry, finish it here. Then when you turn it and do it again, it doesn't intersect itself, right? Turn it, it doesn't intersect itself. So that's the 1st stage. Sometimes that's called stage 0. This is a 2nd stage, or sometimes called stage 1. This would be the 3rd stage. Okay, so if I call this guy H, the thing I want to create is going to be called H. And H is not any particular stage, but it's what happens if you keep doing this over and over and over again. Because notice, this thing is not a fractal. I'm sorry, is not a reptile. This guy here, just in and of itself, is not a reptile. Because if I make 8 copies of it, you know, and do this, well, this is not the same as that, right? It's different than that. So the idea is at each stage, it's not a reptile. But if you do it in the limit, so if you do it an infinite number of stages, or look at the trend as the number of stages go to infinity, that object at the end actually is a reptile. So how we sort of how we think about that is, let's call this guy H1. Sometimes I like to call it H0, the first one. I'll just call it 1, just use natural numbers. Then this guy is H2. And then this guy would be H3. And we could even think about sort of recursively, how do you go from one stage to the next? And I'll say it, but basically from one stage to the next, each segment gets replaced by 8 segments that have, you know, been shrunk down. So if I want to do the next one, each of these segments is going to be replaced by something that looks like this whole thing, but shrunk down a quarter. So that's how you kind of get the next one from that. And once you have that idea, then you make this sort of definition. We say that H is the object that you get if you keep looking at what happens to each stage as the number of stages goes to infinity. So for the 341 students who have had calculus, or the 240 students that have calculus, this notation looks familiar. If you haven't had calculus, the idea you can have without the full-blown calc class. It's just this idea of we're not thinking about what happens at any particular stage. We're sort of thinking about what's the object if I keep doing this over and over and over and again. So it'll get more and more and more wrinkled up, more and more wrinkled up. And the idea is that this guy, this is a reptile. Okay, the other sort of thing to think, they like to call it self-similar. Sometimes reptiles, you know, you only think of those as sort of solid polygons. So it's a self-similar object. And self-similar means sort of like the reptile. So we've got a self-similar object, and it's not any particular stage. It's the limit of this as I do it over and over and over and over and over again, which of course I can't do, but mathematically we can think about. And now we can think about what would be the dimension of this guy. And so I like to think of building them up, but actually what we're doing is we're cutting it down. You get the same thing either way, but let's think about it this way. If we have a self-similar object, we have this nice relationship that the number of copies equals the linear scale factor to the power of the dimension. Again, I like to emphasize that it's the linear scale factor, so I write the word linear in it. A lot of times you won't see that. D is dimension. And, you know, keep in mind, this is not the only way to define dimension. In fact, this is a very limited way. This is a way that only works for these self-similar objects. Okay, so now let's do it for our H. Our H guy which would be the limit of this, each time I need 8 copies to make the next one. So n is 8. So for h, n is 8. And each time I make it, notice it's 1, 2, 3, 4 times. 4 times as long. So S is 4. And then the question is, what would D be? So it's a really nice kind of algebra 2, or maybe pre-calc, depending on where you're doing it, sort of question, right? I use this formula and I plug in these numbers and you get 8 is 4 to the D. And you notice, oh, that is 4 to the first power is just 4, so it's bigger than, D is bigger than 1. 4 squared is 16, so it's less than 2. So whatever D is going to be, it's going to be some number between 1 and 2. It's not going to be an integer. So we know now that H is a fractal. Again, a fractal is an object that has non-integer dimension. It doesn't have to be a self-similar. Okay, if we want to solve this, well, we use logs. And let's take the log base 4 of each side. Of course, the reason we take the log base 4 is because this thing all becomes D. So this gives us log base 4 of 8 equals D. And now, let's see if we can figure out what is the log base 4 of 8. What is the log base 4 of 8? So that's the same thing as saying 4 to what power equals 8, right? 4 to what power equals 8? 4 to what power equals 8? What do people think? Do you know that one? Well, maybe this will help. What if I rewrote this as log base 4 of 4 times 2 equals D? Then we'd get, should I give myself more room? Then we'd get log base 4 of 4 plus log base 4 of 2 equals D, right? Well, again, this guy's just 1. So I get 1 plus log base 4 of 2 equals D. Okay, that might be easier to think about. What is the log base 4 of 2? So that's saying 4 to what power gives me 2? Oh, square root of 4 is 2. So actually this guy here, this is a half. Right? 4 to the 1/2 power gives me 2. Therefore, log base 4 of 2 is a half. So 1/2 is D. So it's really kind of cool that we get, not only is it a fractal, a non-integer one, but it's one of the ones where the dimension is nice. A lot of times the dimension is some really strange looking number that you get from a logarithm. And in fact, let's say I wanted to solve, let's say it didn't turn out to be a nice number and I couldn't solve it this way. Well, then the other way to solve it would be up here. I've got 8 equals 4 to the D. And then you've got D equals the log base 4 of 8, same thing. And again, if I want to put this in a calculator, my calculator doesn't do all that nice stuff. Remember the change of base formula. This would be natural log of 8 divided by natural log of 4. And if you put this guy in, it's going to be 1.5. Okay, so that's kind of cool. Let's look at this thing again. So again, it's not this. It's not the stage 3 object. It's, you know, you go stage 4, stage 5, stage 6, and it gets more and more and more wrinkly. And what happens, definitely you see stage 3 is just one-dimensional. It's, you know, wrinkly, but not, it's still a one-dimensional curve. So in the limit, it gets so twisted up that it actually builds up a little bit more dimension than just one-dimensional. Now, it doesn't get all the way to two-dimensional. In fact, it gets halfway between. So by this measure, it's sort of 1.5 dimensional, right in the middle of being one-dimensional and two-dimensional. So the people that use these curve things for practical reasons, like coastlines and that kind of stuff, it sort of measures the roughness of the object you're studying. So pretty cool. I don't know. So here's a nice example again of a reptile that is a fractal, and kind of the idea of using this formula to figure out this type of dimension.